Today's story is actually another excerpt. If you remember, excerpt is a part from a larger text. And instead of being part of a book, today's excerpt is from a science article. So it's part of a science article by Cheryl Bardot. Here's a little bit of background on Cheryl. For many years, it was nearly impossible to study life at the bottom of our oceans. Therefore, very little was known about the deep sea habitats. But recent 20th century technological advances have allowed scientists to begin to discover surprising forms of life in the ocean depths. In her writing, Cheryl Bardot likes to draw back the curtain to reveal how scientists explore the unknown. She presently lives in Chicago, Illinois, where she once worked at the city's famous Field Museum of Natural History. This is an excerpt from an article called Living in the Dark. And this is coming from collection 4 in your book on page 201. Imagine the moment when a great blue whale, undernourished and exhausted from migrating, grunts out its last breath somewhere in the Pacific Ocean. Then, as the pressure of the surrounding water squeezes the last air reserves from the whale's lungs, this massive creature begins to sink. It plunges 700 feet or 200 meters through the ocean's top layer, the warm sunlight zone, where algae kickstarts life's food chain with photosynthesis. It drops another 2,600 feet or 800 meters through the cold twilight zone, where no plants live and fish have extra large eyes to catch the faintest glimmers of sun. It descends down, down, down through 3,300 feet or 1 kilometer or more of the midnight zone. Here, temperatures hover close to freezing. Deep sea creatures must flash their own lights to break the darkness, and the weight of the water feels like about 500 bowling balls pressing in on every square inch of the whale's carcass. The tiny flecks of dead plankton that are called marine snow may drift for months before reaching the ocean floor. But this great blue whale plummets so quickly that scavengers barely get a nibble. Its 160-ton carcass thumps down nearly intact, depositing as many nutrients as several thousand years' worth of marine snow, all in one fell swoop. This cache of resources, and a cache is an amount of something that has been hidden away, this cache of resources, called a whale fall, will become the center of a unique habitat. First, it attracts deep-sea scavengers. Hagfish, unsightly creatures, also called slime eels, wriggle inside the carcass and begin to eat it from the inside out. Squat lobsters, sleeper sharks, and crabs tear at the whale's flesh and scatter crumbs into nearby sediments. Then mollusks colonize those sediments. Meanwhile, fantastical worms, slugs, and bacteria bore into the whale's bones to feast on fatty marrow. Finally, come bacteria that transform the chemicals leaking out of the decaying bones into food for themselves and others. Much as plants use energy from the sun to make their own nourishment, these chemosynthetic bacteria use energy from chemical reactions to create the basic building blocks of life. Within months, this whole whale carcass may support more than 40,000 creatures. It might keep this chemosynthetic ecosystem going for up to a century. Century is 100 years. The living things that take up residence on this whale fall are similar to those that live near undersea geysers, also called hydrothermal vents. A geyser is a natural hot spring that shoots hot water and steam into the air. And they're also described as cracks that leak natural gas into the ocean, called cold seeps. Together, these three habitats have completely changed how scientists think about the basic rules for life. For most of human history, the ocean's secrets have been beyond reach. Gazing across the water's rippling surface, who could have guessed what truly lay beneath? In the 1840s, British naturalist Edward Forbes dredged the Aegean Sea 100 times to find out. The deeper his device went, the less it dragged up, and Forbes concluded that nothing at all lived below 1,600 feet, or 500 meters deep. This theory fit perfectly with what others had observed on land. If the extreme climates of the Arctic and high mountain peaks snuffed out life, then the cold, dark, deep sea must be empty too. Over the next century, people challenged this theory. Corals were hauled up from 2,500 feet, or 750 meters deep. Starfish and oysters were gathered from 7,500 feet, or 2,300 meters. One expedition collected 4,700 new species from as deep as 16,000 feet, or 5,000 meters. That's more than 3 miles underwater. Because photosynthesis isn't possible at such depths, scientists decided that marine snow provided the base of the food chain for these animals. Sure, they acknowledged life was possible in the deep sea, but scientists assumed that life forms living off such scraps would be meager, meaning very small or deficient in quantity. And so they continued to believe that life couldn't survive in the most extreme ocean floor conditions. Then everything changed. In 1977, a team of geologists squeezed into the research mini-sub called Alvin, hoping to confirm whether geysers, like Old Faithful in Yellowstone National Park, existed on the ocean floor. The hydrothermal vents were there, all right. So was a Garden of Eden, quote unquote, as the scientists called it, of mussels, anemones, and 7-foot worms with crimson feather-like plumes. The stunned researchers gathered samples and called biologists at the Woods Hole Oceanographic Institute, or WHOI, in Massachusetts. It was predicted that vents would exist, explained Santiago Herrera, a biologist currently working at WHOI. What wasn't predicted was that there would be anything living there. Scientists had found an ecosystem that didn't rely on the sun for energy. Not only that, but its inhabitants were thriving in a place that would be toxic for any other known organism. Ideas about the origins and requirements for life on Earth were suddenly turned upside down. You can often find undersea volcanic activity where Earth's tectonic plates are pulling apart. If you guys remember from geography or from science class, tectonic, if something is tectonic, it relates to the deformation of Earth's rocky crust. And so these undersea volcanoes are where the Earth's crusts are starting to separate. As the planet's crust stretches thin, molten rock breaks through to create new crust. Meanwhile, water soaks into the crust through nearby cracks, dissolving rocks and heating up to temperatures of 660 degrees Fahrenheit, before rising again through a chimney on the ocean floor. When the mineral-rich, superhot water from the geyser meets the oxygen-rich, frigid water of the deep sea, a chemical reaction is triggered that forms hydrogen sulfide. This smells like rotten eggs and looks like black smoke spewing into the ocean. Scientists now know that some bacteria release energy by breaking down these sulfides spewing from the geysers. These same bacteria then harness that energy to turn carbon dioxide and oxygen from the ocean water into sugars. That is, food energy. Ta-da! Here's the foundation for an entire deep-sea food chain. These chemosynthetic bacteria may be found for other creatures themselves, or may live in symbiosis with other mouths or stomachs. but get their food by hosting billions of bacteria within their bodies. Many clams and mussels living near these vents get their food the same way. Hydrothermal vents have been a constant source of surprises, ranging from the single-celled microbe that actually lives inside a vent and tolerates temperatures of 250 degrees Fahrenheit, to the white crab with such furry arms that it was dubbed the Yeti crab. Scientists discovered a second type of deep-sea chemosynthetic habitat in 1984. This time, bacteria were breaking down the hydrogen sulfide and methane that oozed from cracks in the ocean floor near Monterey Bay, California. Scientists have since identified 3 sources for these cold seep communities: large deposits of oil or natural gas beneath the seabed, deep trenches created by one tectonic plate sinking below another, and undersea landslides or erosion that expose chemical deposits in the seabed. Cold seep communities play a major role in shaping Earth's climate, Herrera says. If they did not exist, a lot of methane would end up in the atmosphere. Without bacteria breaking down methane from the ocean floor, this greenhouse gas would escape from the ocean and make Earth warmer. Cold seep habitats develop like those at hydrothermal vents do, but with different species. Chemosynthetic bacteria arrive first, forming large white mats on the seafloor. Crabs and shrimp come to scavenge dead bacteria, and mussels arrive that live within symbiotic bacteria. Over time, the chemosynthetic bacteria produce a hard material called carbonate, which offers tube worms a firmer ground to grip than the muddy seafloor. Then tube worms build up their hard protective branches, providing living space for even more organisms. So far, whales are the only animals we know of that can affect life on the ocean floor the same way shifting tectonic plates do. Besides their hefty size, whales are unique in that fats make up 60% of their bone weight. For comparison, humans are born with almost no fat in their bones. In life, this bone fat helps whales float and store energy. In death, these fats are decomposed, meaning they decay or break down, by bacteria that give off hydrogen sulfide. Sound familiar? Once the chemosynthetic community that lives off these sulfides is in full swing, whale falls host an average of 185 different species, the highest number yet observed in such deep-sea communities. Whale falls might explain how species travel across vast ocean spaces from one hydrothermal vent or cold seep to the next. There are specialists in each habitat, but there's also overlap, says Craig Smith, a professor at the University of Hawaii, who discovered the first whale fall in 1987. Some species may use whale falls as stepping stones. Smith says that seeing the same kinds of communities at hydrothermal vents, cold seeps, and whale falls shows us how connected the oceans really are. The connectivity is across widespread spaces from seemingly isolated habitats. 35 years have passed since the discovery of the first hydrothermal vent, but study of the deep sea has really just begun. The main obstacle is getting there. Fieldwork in the ocean requires tremendous resources. For starters, scientists need a ship and a crew. Reaching a field site may take weeks at sea. Then scientists need high-tech equipment to open a window onto the watery world. Even if everything comes together, success is at the whims of weather and waves. Herrera remembers one expedition where an unmanned, remotely operated vehicle called a rove drifted into the wrong place at the wrong time and was destroyed by the ship's propellers. Every time you put something overboard on a ship, he says, it's basically a miracle that you get it back. Under such conditions, scientists must balance the thrill of discovery with persistence and patience. Smith knows what that's like. His team discovered the first whale fall at the tail end of the last Alvin dive on a research trip. Within 10 minutes of Alvin's return, we knew what we had, he says. But we had to wait a year to get back and to investigate it. Fortunately, improvements in technology are giving scientists more ocean access than ever. In 2010, Herrera sailed to the Coral Triangle near Indonesia. This is the most diverse marine ecosystem on the planet. And scientists wonder if the deep sea communities underlying the coral reefs there might be the reason. Herrera was one of only a few scientists on the ship, but video footage of his rove dives was transmitted to Massachusetts, Maryland, and Washington, plus Canada and Indonesia. Dozens of scientists worldwide witnessed and discussed the dives as if they were all present on the ship. The goal of this expedition was to explore unseen waters and identify places worth returning to for in-depth research. Scientists saw far more than they expected. Monitoring video from most exploratory dives means watching hours of flat and empty, which is to say boring, seabed scroll by, hoping to spot something exciting. But on this expedition, Herrera says, we were never bored because we were constantly seeing amazing species. We suspect this is one of the areas of highest biodiversity on Earth. Scientists will definitely be going back just as soon as they can find the money to fund another expedition. To date, scientists have identified more than 1,300 species in deep sea chemosynthetic habitats. These organisms have introduced us to completely new ways of life and expanded our view of how adaptable life can be. Yet they raise as many questions as they answer. Smith predicts that scientists will be finding life popping up in even more surprising locations. We haven't exhausted the list of processes that create these kinds of ecosystems. The oceans cover 70% of Earth's surface, yet less than 5% of this resource has been explored. This is definitely worth investing your whole life to study, Herrera says.